So welcome everyone to the, can you hear me? Someone please confirm?
Yes, I can hear you.
Okay, perfect. Okay.
Yes, we can hear you.
Okay, so welcome everyone to this tutorial on gap-free verification of processor cores. And my name is Kirti Devaraja Gowda, and I'm currently with Infineon Technologies. And my colleague is Mohammad R. Fadihe. And Mohammad is currently with TU Kazakh and he's pursuing his PhD there. And so this technique, we call it as C-S²QED, and C here stands for complete, and S²QED stands for symbolic initial state, symbolic quick error detection. So why such an acronym? Because so this technique was originally called as QED, quick error detection, that was used for post-silicon validation. And so together with Kaiserslautern, Stanford, and Infineon, through this collaboration, we extended this approach to be applicable on pre-silicon verification, and we extended with symbolic initial state using formal tools, and that's why we call it as, and also the term complete is because this approach finds all bugs in a processor core, so that's why the overall name complete S²QED. Okay, so the outline of this tutorial is as follows. In the beginning, I will briefly motivate our work on processor verification. And then I will introduce some terminology with respect to the processor bugs, like what are the different types of bugs that can occur in a processor core. And afterwards, I will introduce how the C-S²QED approach works and how does the property look like by taking an example. And we already use this approach to verify a set of RISC-V cores. And I will show some experimental results we were able to obtain so far. And followed by a live demo. Mohammed will do a live demo using a RISC-V design, and he will show how the C-S²QED approach can be used to verify a RISC-V design. And he will also show different aspects of the verification. And in the end, we will conclude this tutorial with a brief summary. Okay, so pre-silicon verification, I think nowadays every verification engineer, they know very well that pre-silicon verification is one of the most resource-intensive tasks in the development cycle. And it's well known also that today we are trying to verify our designs. We are running against the time, trying to get our designs verified within the timelines. And it's not very uncommon if these deadlines are not met and always extended. And why is that? Because the main reason is that the designs are becoming more and more complex, and we need more time to do the verification. And going forward, since we know that the designs are not getting any simpler but complex, the existing methods, they may not be sustainable anymore. And when it comes to, when it comes to processor verification, the situation is even more worse because the processor verification, the cores, due to microarchitectural optimizations, they're probably the most complex designs that we work with. And as it's shown on the screen, the verification itself consumes at least 70%, and usually it's more than 70%. And moreover, not just the timing, the verification engineer, he needs to have a very good understanding of the microarchitecture, and he needs to have a very good experience with verifying processor cores, because some bugs are hard to find, and the verification engineer, he has to create specific stimuli and trigger them so that all the bugs are found. And so that's the main reason, because with simulation, it's almost impossible to trigger all possible combinations of instruction scenarios. The simulation may not be enough to completely verify the processor cores. So let's consider an example. And here is an industrial microcontroller core that was built at Infineon. And the ISA of this core or controller, it specified around 60 instructions. And the RTL implementation itself, it included around 1800 flip-flops. And the microarchitecture of this controller was highly optimized for specific safety applications. And on the right, you see these are some of the applications that this controller is being used in. It is already in the field in many cars. And 3D cameras, airbags, and tire pressure monitoring systems. So these are some of the examples where this controller is being used in. And how did the verification effort look like? So here is a table that is shown. In the first column, we have the different verification method. And in the middle column, we have the effort that was required to verify the initial version of the RTL. And on the last column, we have the effort that was required when the RTL was updated. For example, when this RTL was used for a different application, some additional features were added in. And the last column shows what was the effort to verify the additional features. And so the directed simulation, so this is not necessarily a verification setup, but it's something that the design engineers did. And so the design engineers, they spent around 10 to 12 months for the whole design process. And our designers informed us that most of the time, at least 50% of the time, they were doing the verification. That means they were writing the directed stimuli to check if the design is behaving as expected. And the main method for the verification of this controller was constrained random simulation. And in the beginning, for the initial RTL, it took around 12% months. And for the updated RTL, depending on the amount of changes, it required around 3 to 6% months of effort. And we also did formal verification with 100% code coverage and 100% functional coverage. And for the initial version, it required 5% month. And for the updated version, it required around 1% month of effort. So even for such a small microcontroller code that had only around 60 instructions and 1800 flip-flops, we needed a huge verification effort to finally tape out this design. And knowing that due to Internet of Things, machine learning, AI applications, smart cities, since the processors are going to become more and more complex, these techniques, if we still continue doing the verification as we are doing now, they may not be sustainable. And we definitely need new methods for verifying processor cores. So that's the summary, what I wanted to convey with the current existing methods. So what we are proposing today is a complete S²QED. And as I said, complete S²QED is based, it uses formal verification, and this approach is highly automated. And this approach, complete S²QED, it extends a previously known technique called S²QED to satisfy the completeness criteria. So here, the completeness criteria, it's a methodology proposed by OneSpin. It's also called as gap-free verification. And it's a methodology which proposes how to write a set of properties that completely verify the design. That means a set of properties that have no holes in it. Okay, so we call it complete because it detects all functional bugs during pre-silicon verification, so that during post-silicon validation, we only have to worry about electrical bugs or some other timing glitches. And so the main benefit of this approach is that we need a very simple property set to find all the bugs. And that means the effort requires low manual effort, and also a verification engineer, it doesn't need to be a formal verification expertise to implement this approach. So yeah, so these are the main highlights of this approach. So now let's see what are the different aspects of this approach. Okay. So yes, so before going into the approach, let's take a look into the type of bugs that can occur in a processor core. There are two types mainly. The first one is single instruction. The second one is multiple instruction bug. So now let's see an example for the single instruction bug. So here is an example program, and the mnemonic here stands for branch if not equal to. What it does, what this instruction does is it compares the contents of register R1 with that of R2. And if these contents are not equal, then the PC becomes PC is equal to PC plus 20. 20 here is the immediate value. And if the contents are equal, then the branch is not taken. The PC simply moves to the next instruction. So that is the semantic of this instruction. But now let's assume that there is a bug in the core. So now let's assume that there is a bug in the branch control. And regardless of the values, the branch is never taken. So in this example, the R1 has all ones and R2 has one. Certainly, these two contents are not equal, but the core doesn't take the branch, but it simply moves to the next instruction. That means there is a bug in the core, and the BNE is not executed properly. And this is an example for a single instruction bug. And why we call it a single instruction bug is it doesn't depend on the program context. And what do I mean by program context? So in order to find these bugs, or for this bug to be triggered in a processor core, a sequence of instructions. So whatever the instructions that were executed before this instruction are irrelevant. So whenever the processor core gets this instruction, regardless, even if the contents of the R1 and R2 are not equal, the branch is never taken. So that is the bug. And these type of bugs depend only on that specific instruction. So now let's see the second type of instruction bug. We call it as multiple instruction bug. And again, there is an example here. And so the first instruction is a load word instruction. What it does, it computes the address of the memory by adding the contents of R3 with an immediate value 1. And from the resulting memory address, it fetches the value and then loads that value to the register R4. And this instruction is followed by an add instruction, and it simply does the addition of R3 with that of R4, and then it stores the result in R2. So now what is important here to notice is there is a direct dependency between these two instructions, which is the results of the instruction, load instruction, the destination register is R4. Again, for add instruction, that R4 itself is the source register. So the core has to wait until the value in the R4 is available. And in case if the hazard detection or if the forwarding is not working properly, then we have a wrong behavior there. And now these two instructions are followed by three more instructions. The next two instructions are nop nop. That means the code does nothing, followed by the same add instruction. So again, the value of R4 is added to R3 and the results are stored in R2. But here, if we look at here, this instruction has no dependency with the previous instruction. That means there is no stalling required, no forwarding required. The value is simply fetched from the register file, and then the results are stored to the R2. And so we call these type of bugs as multiple instruction bugs. The main reason is, so here in this add instruction, this first instance of add instruction, the bug was triggered only because it had a dependency with the previous instruction. That means whether the bug will be triggered or not, it not only depends on one instruction, but also on a sequence of instructions that were executed before. And so this sequence of instructions, we refer to them as program context here. So yes, so these are the two types of bugs that can occur in a processor core. And the summary is as follows. A single instruction bug, it consists of one instruction. And in this example that we looked at, that instruction is BNE that activates the bug. And the same instruction propagates the bug into a program visible register. So here, program visible register refers to a program counter, a register file, or control and status registers maybe. So the same instruction activates and propagates the bug into a program visible register in case of single instruction bug. And in case of multiple instruction bug, we have a sequence of instructions that activate the bug, not one instruction, but a sequence of instruction. And here in this example shown, load word followed by an add instruction is a sequence of instruction that triggered the bug. And then we have one instruction that propagates the bug into a program visible register. And in this example shown, add instruction is that instruction that propagates the bug into a program visible register. So this is the summary. And if you find any bug in a processor core, this bug can be either categorized as a single instruction bug or a multiple instruction bug. So now let's see how we set up the verification setup to find both type of bugs. Okay, so let's consider a pipeline processor core. And yes, of course, I mean, if you have a single stage core, the verification is not so difficult because we don't have to consider all complex scenarios of forwarding, hazard detection, and so on. So It's a reasonable assumption to make that most of the cores today are pipeline processor core. Let's consider pipeline processor core, and we duplicate this pipeline processor core, and we make two instances of the same core. So here CPU1 and CPU2, so they are the identical instances of the same core. And at arbitrary time point TIF, so IF here stands for instruction fetch. At some arbitrary time point, they fetch the same instruction. And here IUV stands for instruction under verification. They fetch the same instruction. And from our examples of the processor bugs, so this instruction under verification is the bug that propagates, sorry, it's the instruction that propagates the bug into a program visible register. And the only difference between these two instances is that they are configured to start from different states. And how does it look like? How do we do this? So let's say this is our core, and we simply have to write a top module which instantiate the cores twice, and we call it a CPU1 and CPU2. And this top module also feeds the instruction memory and data memory interfaces to the corresponding core instances. And yes, so as I said, the only difference between these two core instances is the starting state. So ST1 is the starting state of CPU1, and ST2 is the starting state of CPU2. And what is ST1? ST1 is a flushed pipeline state, which simply means that at this time point, TIF, there are no other active instructions in the pipeline. It doesn't mean that this is a reset state. Of course, it could be a reset state because right after reset, there are no other active instructions in the pipeline, but it can also be any other state. The core can execute certain number of instructions, and then it can come to a state where there are no other active instructions in the pipeline. And on CPU2, the state is ST2, and there is no constraints. It can be anything. That means the core can previously execute any instruction, and at TIF, there could be other instructions that are active in the pipeline. So how do we write this in a property? And this property is written in an interval property syntax, ITL. And so let's assume this is the macro CPU1 fetched instruction that returns the instruction that is fetched to CPU1, and we assume that this is the same as CPU2. And on CPU1, we say that flushed pipeline state. And how do we realize it? It's actually very simple. We simply have to assume that TIF, let's assume TIF is time point T. Then T-1, T-2, T-3, we simply have to force knobs on the instruction. So that's one way to realize a flushed pipeline state on CPU1. Okay, so this instruction that was fetched at TIF, this is decoded in the next clock cycle, which is the instruction decode. And at this time point, we know what is the type of instruction. And here we assume that for one example, we assume that this instruction belongs to register type. That means the operands are coming from the register file, and the operation is some arithmetic or logical operations. Okay, so this is the initial setup. And so now within the formal tool, these two instances are unrolled as long as the execution time of an instruction. For example, if we have a 5-stage processor core, then it is unrolled for 5 to 6 clock cycles or even more, depending on the stall states within the pipeline. And here, this is an example. So TIF instruction fetch, decode, execute, memory access, and write back. And in the next clock cycle, write back +1, the results of that instruction, IUV, are visible. So this is how the verification setup looks like. And one more assumption what we make is on CPU1, we again enforce starting from TID, it only fetches NOP instructions. And this constraint is not really important when it comes to finding the bugs. It's only important so that we reduce some complexity for the formal tool. Otherwise, there is no relation with respect to the processor bugs. And again, on CPU2, there are no other constraints, and any instruction can be fed into the CPU2 instance. Okay, so this is how the verification setup looks like for the C-S²QED. Now let's see how the single instruction box will be found by this verification setup. And for the single instruction bug, let's consider only the CPU1 instance. And if we consider this instance, a TID, as I said before, is the time point or is the stage of the instruction execution when the source destination registers or immediate values or operations to be performed are decoded. So at this clock cycle, we know what this instruction will do in the pipeline. And at time point TWB, if it's an add instruction, then the results of the summation is written to the register file at this clock cycle. So the value is being written to this core at this clock cycle, but if we probe the register file in this clock cycle, the value is visible. And if you remember, we made an important assumption on the CPU1 instance, which is that it starts from the flushed pipeline state, ST1. And a flush pipeline state, it means that there are no other active instructions in the pipeline. That also means this instruction has no dependency with the previous instructions. So that means we can simply add in the proof part a simple macro to find out the results of this instruction execution. So here, as I said, TWB plus 1 is the clock cycle when the results of the instruction execution are visible in the register file. So here at this time point, we have a macro, and the macro on the left-hand side, it simply probes the register file with the destination address at time point TID, because remember, at the decode stage, we know which is the destination register. And on the right side, we have a macro expected value. And to this macro, we have to pass some arguments, and these arguments again are which are the source registers and what is the type of instruction, whether it does addition, summation, logical operations. So the first argument says which operation is performed, and second and third arguments say what are the source registers. So these the right hand side, this macro can also be directly derived from an executable ISA model. And so when we have this property, and if this property fails, that means this is a failure only because the instruction itself is not behaving properly. And it has no relation with respect to other instructions because we started from a flush pipeline state. And these type of bugs are again single instruction bugs, and all the single instruction bugs that are associated with register type instructions will be found by this property. So this is the one property that is needed for the entire instruction class. And for detecting other instruction classes, we simply need a similar property with other instruction classes, but then we need a different macro here to specify the type of operations performed by that specific instruction class. And as I said, again, these macros, they can be automatically derived from an executable ISA model. So that's about a single instruction bug. How do we find it? It's very simple to write this property, and we don't have to consider all complex scenarios in the pipeline because we started from a flush pipeline state. Now let's see how can we find multiple instruction bugs. So for the multiple instruction bugs, we have to consider both the instances. And again, I would like to remind that in case of both single instruction and multiple instruction bugs, the instruction verification is the instruction that propagates the bug into a program visible register. And for the multiple instruction bug, additionally, there is also a program context. That means a sequence of instructions that were executed before that activates the bug. So, so how do we create a scenario such that all the multiple instruction bugs are triggered? And so for this, in order to achieve this, what we need to do is we have to create a scenario. We have to create a scenario on CPU2 such that it gets the same operand values as CPU1. So remember, in case of CPU1, because we started from a flush pipeline state, the values are fetched from the register file. But in case of CPU2, it is symbolic and it can execute whatever the instructions it wants to before the time point TIF. So the value may be coming from the register file, or it can also coming from the one of the pipeline stages, maybe a forwarding unit. And we need to create a scenario such that even though the value comes from the pipeline, the value has to be same as in case of CPU1. How do we do that? To do that, it's again important to consider this time point, TWB. So again, at this time point, the results of the instruction under verification are committed, and these results are visible at the next clock cycle. But now at this clock cycle, the results of the previous instructions, that means the instructions that were executed before the IOV, they must have committed already in the previous clock cycle, and those results are visible in this clock cycle. So now, in order to make that even the CPU2 gets the same operand values, we have to assume that at this clock cycle, CPU1 and CPU2, they are consistent. What do we mean by consistent? So it's a simple assumption which simply says that the register file, the contents of the register file on CPU1 are equal on the contents of the register file of CPU2. So this is a simple formula to represent that. And in a property at TWB, we assume that both the CPU1 and CPU2, they're consistent. And so this, again, as I said, this assumption is important to say that both CPU1 and CPU2, they get the same operand values. And also, if you remember our terminology of the bugs, IUV propagates the bug into the program visible register, but the instruction that were executed before, they may trigger the activate the bug, but they don't propagate the bug into the program visible register. So they are anyway expected to be consistent. That means they're expected to have the same results both on CPU1 and CPU2. So now to complete this property, what should happen at time point TWB plus 1 when the results are actually visible in a bug-free processor? Because we assume that both CPU1 and CPU2, they get the same operand values, even in the next clock cycle, they should again lead to the consistent state. And how do we capture that in a property? Again, it's the same class, consistent registers, but instead of TWB, we put it in the proof part, and we put it at the time point TWB plus 1. So now this is the whole property and the C-S²QED property, and this is the C-S²QED property for the instruction class register type. And as I said, the first class here, CPU1 reg is equal to the expected value. This class will find all the single instruction bugs associated with this instruction class, and the class consistent registers, because we assume again to be the operand values to be the same. Again, at time point TWB plus 1, the register files are again expected to be consistent. And if they're not consistent, that means maybe the forwarding didn't work properly, maybe the hazard detection didn't work properly. And because we are using the formal tool or the formal technique, all the instruction combinations will be checked such that the formal tool will try to fail this property. In order to fail this property, it will consider every possible instruction combination. And while doing so, only when all the instruction combination doesn't lead to a failure, this property passes. And when this property passes, that means our core is free of any multiple instruction bug or single instruction bug. So that's the C-S²QED property we need to verify the instruction class belonging to register type. And we need such properties also for other instruction classes. For example, if it is a load instruction class, then we need one more property. And in general, if we have a core that is implementing 10 instruction classes, then we would need 10 C-S²QED properties. So this is how the verification setup and how the C-S²QED methodology works. So now let's look at some experimental results. So we already applied this technique to verify a RISC-V processor core currently being developed at Infineon. And as this naming shows here, so the core has a base ISA, with extensions, compressed instruction extension, multiply extension. X here stands for custom instruction extension, and also CSR instruction extension. And the microarchitecture of the core looks something like this. It's not the exact representation. And so again, it has two separate interfaces. Basically, it has a hardware architecture, an AHP interface with the memory and the instruction memory, and again, an AHP interface and the data memory. And it also has an instruction FIFO to save some clock cycle in the instruction fetch stage, followed by the decode stage. The decoding and the hazard detection takes place at this clock cycle. And in the execute stage, in case of load instruction, we access the memory, and the value from the memory is read in the next clock cycle, which is our next stage, which is memory access stage. And depending on the type of instructions, other operations are performed in the execute stage. And finally, in the write back stage, the results of the instruction execution, depending on the type of the instruction, they are returned to the register file. So this is how the architecture of RISC-V core look like. And so these are some of the results. So before using this or applying this C-S²QED approach, we previously verified this core using the CIPC approach. So for those who don't know what CIPC stands here, it stands for complete interval property checking. And again, it's a completeness methodology proposed from OneSpin. It's also in the industry, it's also known as gap-free verification. It's a methodology that proposes how to write a complete set of properties without any gaps in the property set. And again, so this methodology if implemented properly, it's a foolproof methodology, and it detects both single instruction and multiple instruction bugs. And effort-wise, for the base instruction ISA, it needed around 16% days to write the properties, and to make or either to get a pass or fail on the design. And for the new extension, it required around 5% days. For example, if I have the CSR extension, then I needed 5 more % days to implement the properties and make sure that the properties are holding or failing. And when it comes to the property runtime, on an average, it took around 30 seconds for the properties to hold whenever there was a bug in the property or in the design. And so counterexample length is also very important when it comes to debugging. And let's say, I mean, if I have a property failing, and if the counterexample has 20 to 30 instructions, then it's very difficult to understand what is the root cause of this failure. So in that sense, the number of instructions that were there in the counterexample were fairly minimum. In case of single instruction bug, we had to look at only one instruction. And in case of multiple instruction bugs, we had to look at 5 instructions, which is fairly reasonable for the debugging. And afterwards we applied this technique, and so again, these are the numbers. As I said, this technique or approach also detects both types of bugs. And so this is the major advantage of this method, even with such a small effort. That means for the base ISA, we needed only 5% days of effort to get the properties holding. And for the additional ISA, because depending on the type of the instruction extension, we only have to change the macro that is written in this property. And that means it requires very less time for implementing. And again, when it comes to the runtime and then the counterexample, it has a similar effect as CIPC. And moreover, what was interesting with C-S²QED was, so if you remember our CPU1 instance, it was starting from a flush pipeline state. That means we were very sure that there are no stalling scenarios or hazard scenarios that can occur. So that meant we could be very strict with the time points. And because we were strict with the time points, we found out that the core was stalling unnecessarily. That means there was a scenario when the core didn't need to stall, but it was stalling. Functionally, it is okay, but for performance, it was not okay. So that's why we call this as a performance bug. And with C-S²QED approach, these type of bugs were also were found. Okay, so that's about the C-S²QED approach and some experimental results. So now I think Mohammed will do the live demonstration. Mohammed, I think you can already start sharing.
Yes, okay, I will try. So, can you see my screen now?
Not yet. Maybe I stop sharing first. Yes, I think now we see your screen. Yes.
Okay, okay, great. So, hello everyone, I'm Mohammad Fadi here, and I will present a quick demo on how we can use a C-S²QED approach to verify a RISC-V core. This is essentially the one-spin environment that we are using for this demo. Let's start with the C-S²QED top module, which is the top module in our verification environment, which essentially consists of the two instances of the CPU that was talked about in the presentation. So let's have a more detailed look. Essentially, this C-S²QED top, besides from clock and reset, has two sets of inputs. First is the instruction input, which is used for the instruction stream for each processor, and also the data input, which will be connected to the data stream that is coming from the data memory for each processor. And at the end, when we load this into our verification environment, essentially these inputs will be modeled as symbolic inputs to the overall verification environment. Inside this top module, there are two instances of our CPU under verification. And the important point here is that these two are independent from each other, except for clock and reset. The rest of the inputs are independent from each other, and essentially the data and instruction inputs are connected to the top level inputs, which will be at the end symbolic variables. It should be noted that this is only for verification purpose, and this self-duplicated model will not be actually used in fabrication, just for verification. Using this as the top module, we develop a set of C-S²QED properties, which will be proven on this. As you can see, we have different properties for different instruction classes, for example, immediate arithmetic, load instruction, register arithmetic, and so on and so forth. And you can also see here, for the matter of time, I have them previously proven, but you can see the runtime here that for most of them, it's in a matter of seconds, and just the register and arithmetic type is a matter of minutes, but it's still less than 10 minutes, which is completely reasonable for completely verifying this design. Now let's have a more detailed look into the register arithmetic type. Before I go into detail of this property, I have to mention that the property is written in ITL language, which is a language developed by OneSpin. And the reason we use this is that the actual property at the end is more simple and more readable, so it's more suitable for this sort of demos, but it's not limited to this, although it's also easier to develop the property in this language, but it's not limited to this language. You can also have this property in the normal standard SVA language. And to talk a bit about the syntax here, as I mentioned, dependencies are similar to the assume statements of the SVA. We have time points, which are used to capture events, the time points of events within the time window of the property. And using these time points, you can also freeze values of certain internal signals into local variables. And the property itself has an implication form with an assume part and a proof part. So now let's talk about the property itself. So first, we have these dependencies, which are essentially used for excluding invalid instructions from the instruction stream. So each of these constraints are essentially excluding one invalid opcode for the inputs, for the instruction input. We also don't want to have a reset in the middle of the property. So that's why we have this no reset constraint. And also because we don't have a real instruction memory attached to the system, Here we have this consistent fetch, which ensures that if the instruction fetch is repeated for the same address, the same instruction is being returned to the processor. As it was explained in the presentation, in C-S²QED property, we compare values of different registers at different time points of instruction executions. We need to capture those events. For CPU instance 1, we consider TIF to be T+4, and that's because we want to give time to the solver to feed NOPs to the CPU instance 1 in order to create a flushed pipeline. And because we know that there is no stall in this processor, we can compute the T write back as TIF +3, which is because we have 4-stage pipeline here, and that's information that users should know. And even if it's not really strictly followed by the design, you can find that as a performance bug, as it was explained in the presentation. For CPU2, it's a bit different because we can have a stall here. So we have to check whether there is a stall or not based on this macro that we define. So if there is no stall, it will be the same as TIF of CPU1. Otherwise, we need an additional delay to accommodate the stalling. And once we calculated this TIF, we can also calculate T of execute phase, memory, and write back phase. And at the end, T check is the time point that the values are available and visible at the register file. The property, the assumption of the property, the first assumption is that we need to have the same instruction fetch in both CPUs. So we have the same instruction under verification. And because we wanted to have a flushed pipeline in CPU1, we assume that before and after IUV, only no operations are fed into the CPU1. Also, this is a register arithmetic type, so we assume this is the type of instruction using this macro here. And also for this type, it's not valid to have R0 as a destination register, so that's also excluded here. In CPU2, we have a symbolic program context. So essentially, it's possible to have a preceding branch instruction that cancels the instruction on the verification. We don't want to consider that here because we are interested in the case that the instruction is actually executed. So using this macro, we also ensure that the IUV is not canceled by other preceding instructions. And at the end, we have the consistent register file assumption, which essentially checks, make sure that at the write back time of each CPU instance, the values in the register file are consistent, which means that from ISA level point of view, both CPU instances fed the same operand to the IUV, although in CPU2, it may come from register file or from forwarding unit or some other places. So once we have the assumption in the commitment part, first we have this statement, which is for the single instruction bug, and which checks the result of CPU instance 1 based on this macro, which computes the expected output for this instruction based on the opcode. And the macro itself, there's nothing special about it, just based on the opcode, it select a specific behavior, and in each behavior, we compute the correct output. For example, this is for subtraction, this is for shift operation, and so on and so forth. And it can easily be generated from an executable ISA, and it can also be reused if you have the different design with the same ISA. You just have to redefine the macros here that returns the value of RS1 and RS2. So in addition, we also need to make sure that the instruction does not have an unexpected additional behavior, like for example, an add instruction that makes a memory access. So that's pretty straightforward and standard for most of the instruction. And for multiple instruction bugs, you need to make sure that the output in CPU in the register file in CPU instance 2 at T-check has the same values as CPU instance 1. So also for any program context, the result is the same as the case for the flushed pipeline. And it should be noted that here we don't make any assumption on CPU2 except for the consistent register file. And so the preceding instruction, the context of the pipeline is purely symbolic, and the solver can explore all possible scenarios here. So that's essentially the register arithmetic type, and the rest of the instruction classes are pretty similar to this. But instead of going into the detail of these other instruction classes, let's have a look into an example of how would the counterexample look like in a bogus design. So I'm reloading another design here. And we want to look into the counterexample and how it looks like. So right now, OneSpin is loading the design. So, so the design is now loaded, and we can see that so the proof is running. As it was explained in the presentation, it would take around half a minute to see the counterexample. So now we have the counterexample. This is the debug environment. And in the debug environment, you can see that which part of the property commitment is actually failing to this red color here. So this is the part that has been violated, and we know that this belongs to the single instruction box. And because of that, we only need to look into the behavior of CPU instance 1. And this is essentially the waveform for this counterexample. This is a fetch clock cycle. We can see that, okay, based on the opcode 7 is an OR operation. We can see these are the outputs of the decode unit, the RS1, RS2, and RD, and these are the values for RS1 and RS2. If you go one clock cycle further to the execute phase, we can clearly see that the operands are correctly propagated to the ALU, and also the opcode is correctly propagated, but the result is not actually correct. This is not the OR of these two values if you compute it. But if we look internally into the ALU, you can see that the OR operation inside is actually producing the correct output, but it's not selected. So the logic that is responsible for selecting the right operation at the end for the output of the ALU is not behaving correctly. So it's selecting the wrong result and it's actually writing the wrong results at the end to the register file. So that's how the counterexample for single instruction will look like. And we have to now go to the design and fix this and essentially re-verify the design. But instead of that, let's have a look into other example that I have also preloaded for the matter of time. So this is a different design. And now if we have a failing property, and if we look at the debug environment, this time we can see that this part of the property commitment is violated, which belongs to the multiple instruction box. Now, if we go to the waveform of this one, yeah, so this is the waveform, and this time we have the signals for both CPU instances. So above this this double line, we see this signals for CPU1, and below we see the signals for CPU2. And the red signals are the register file values, which is causing the violation of the property. So here at TIF, if we look at this, we can see that this is a subtraction instruction. And this is the outputs of the decode unit, RS1 and RS2 and RD. And these are the values of RS1 and RS2, which one clock cycle later are fed to the ALU and the subtraction is calculated. And at the end is written to the register file at this clock cycle. If now we come to the CPU instance too, we can see that, okay, the decode unit is producing the same signals. So it's correct as expected. But the interesting point here is that if we look at the address of RS1, which is register 24, and the RD of the instruction for 2 clock cycle before, these are the same. So both of them are 24. So 2 clock cycle ago, there was an instruction that's trying to write to this. And it's actually, if you look at the instruction, it's actually a load instruction. And this one is trying to read this. So this is a clear data dependency that has to be handled by the forwarding unit. And if we go 1 clock cycle further and look into the ALU, to the operands of the ALU, you can see that the RS1, the input 1 of the ALU, is not actually correct. If you compare it to this one, you can see that these are different values. And if we look into the register file for R24, we can clearly see that it's reading the value in the register file rather than the old value, rather than reading a new value that has to be read, because this belongs to the program context before the instruction under verification, and this is the correct value. So we can clearly see here that the forwarding does not work properly for this write back to execute a stage forwarding, and we have to again go into the design and fix this problem. So that was essentially the demo. So to conclude this talk, C-S²QED is a highly automated, gap-free processor verification technique that can detect all functional processor parts. And the big advantage is it does not require developing complex properties. It does not require having high expertise in formal verification, and then it's a fairly low manual effort technique. Thank you for your attention.